the
Recording is on.
high speed and demux chips.
Okay. Well, that's what they are. That's what the FST is.
Yeah.
Actually, it gave me food for thought there, because Dave and I experimented with the 612. Well, Dave did the 612, Dueling 612 project. And the original project had, I don't know what he used for switching I think he was using FETs for switching first and then switched the pin diode, but never got it to work. It never occurred to me at the time, but maybe the FST chip would have been a good chip to do the switching. Instead, we went to relays.
Yeah.
Anyway.
The only way you can find out is try it out.
Yeah. Anyway. I'll be quiet now. I don't have Dwayne. Dwayne was there a second ago.
The problem is, Peter, you got to pay very close attention to capacitance of those chips.
I forget what the capacitance is on those chips. I know the input, the output are 4 ohms, and then they parallel the two of them together, so you're down to 2 ohms.
No, it doesn't matter about that. I'm talking about what the internally you got traces.
Oh no, I
you
understand.
Got the chip.
Yeah.
And inside the chip, you got pads also really close together, and that forms a capacitor.
Yeah.
And so there's a spec they've got. Is it isolation? There's a spec they've got. You got to pay close attention to that. How much dB of isolation you've got? Because if you're using signals that are relatively strong, you put a signal in, it's going to come out the output, even though you've got it switched, so that signal doesn't go through. So you have to be very, very careful with internal capacitance of those chips. And that was the problem with pin diodes, because I used pin diodes, and I wasn't really using a real pin diode, and a diode. It's got a PN junction, which is basically a capacitor, right. And so you'd have signals just going through, bleeding through.
Well, it certainly seemed to work well on receive. Never tried it. Obviously you're not going to put much power through them, but anyway. Huh. All right, I'll leave it to you, Ken.
All right, Mazu. Let's give a couple more minutes and then see who else is going to show up.
Yeah, I'll send yet again another message to Hassan. Maybe he's shy to come on because he's got a new haircut.
I'll be back in a sec, guys.
Hey there. Good evening, everyone.
Good
Eric.
evening.
Good evening, Eric.
Hey. Made it. Recording is on, I think. It seems to be working. Of course, Windows decided to do updates all over the place just prior to, so that was the last half hour of my life.
Haven't you learned your lesson whenever you do these things? Same thing with my guitar lesson. A couple hours before it, I turn everything on, make sure it works.
Well, if I had your kind of retirement, then I guess I could do that. But since I had to work today,
if I had your money, I would have retired 5 years ago.
What airline did you own again? Was it Air Canada or?
I hope you guys are flying with the People's Airlines so you can keep my pension afloat.
What's the airline?
AC.
AC, it is. Yeah.
There you go.
And he was trying to give me mail today.
Who was?
He who shall go shopping.
Who likes to shop? What was I doing to you?
Nothing.
Nothing.
You're offering me. Yeah. Just said. Anyway. Yeah. So Peter, guess what? I broke down, and I guess we're not going to Hamfest anymore. I broke down, and I'm going to Hamfest with them.
Why aren't we going to the Hamfest? It's a double header day. But that's not at 8 a.m.
Oh, okay. Yeah, I guess that's true.
Right?
Well, yeah, so I'm going to my first Hamfest since Dayton.
Wow. Spend money.
No.
Interesting.
He won't be spending any money. I doubt he'll even break a 20.
I know how to get him to spend money.
He's driving. He's paying for parking.
Well, actually, I'm going to meet you there. We have to talk logistics. Anyway, is my video like going bright and dark? Is it pulsating for
Yeah.
anyone else? It is, eh?
Yeah.
That's weird.
Okay,
Need
let's
to
get
pay your power
started.
bill.
The recording's going? Yeah.
It's
Honestly,
a bit annoying. So maybe you should mute your visual. That's big improvement.
Yeah. Honestly, I don't have like.
Okay.
all yours, Ken.
Let's get the show on the road here. Welcome everybody to our main meeting, September the 20th. Before we get started here, we've got to read the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. And before we get started here, speaking of recordings, I don't know if the guys have been reading the thread there, but Microsoft got rid of their video editor, which was excellent as far as I'm concerned, because I could put a video string together in like 5 minutes. And they replaced it with another package that they bought off another company called Clipchamp. And it comes in either an app you install, or you use the web service. I used the app, and it just kept crashing and crashing and crashing. And then I spent about a week. Went through, actually counted them, 13 different video editing applications, and I finally found one that works almost like the old video editor works. I still got a couple things to work out on it, and but we're back to normal now. And it takes just as much time to set up as the old video editor did. So that's it. Tonight we have Dave doing a presentation on his S-meter circuit, and I believe that's with the Phoenix. And then we're open for discussion after that. So go ahead, Dave.
You're muted, rookie.
Yep, I said I'm just trying to change my cursor here so you guys could see my presentation. Oh, here, the mouse pointer. There we go. This is what I want. Yes, this is what I want. Okay, so let me share my screen. So there, you guys should see my screen.
Got it.
Can you guys see my screen?
Yep.
You can see my extra large cursor here.
Extra large.
Yeah, okay. Okay, so yeah, what I want to do is I want to talk about the Phoenix and what I did in terms of making an S-meter for it, what kind of I went through, my thought process, and it's basically my approach to building a S-meter. And just want to caution you, this is not a tutorial. You know, I'm no expert on this stuff. And so I'm going to quote Charlie Morris here as, you know, this is not a tutorial. It's a log of what I did, right or wrong. So I'm not claiming to be an expert. I'm not claiming to be a guru on S meters. So you always need to take whatever I say with a grain of salt. And for you, Ken, with tequila.
Excellent.
Okay, so what I want to do tonight is I want to, first of all, just a brief introduction of what S-meter is. I think as amateur radio operators, we should all know what S-meter is and how it works. I'll talk with some approaches to making using S-meters, and then talk about two techniques in terms of building a S meter. So just as an introduction, your S meter is giving you, a signal level of your receive voltage in a receiver. Can you guys see this okay? Because sometimes I can go to a full screen mode and you can see things a little clearer. I like
That's
using
better.
the sidebar because then I can move around. I could know what slides I need to go and show. But here, so anyway, so a S meter is giving you the received. It's giving you an indication of the received signal that's coming in from your antenna. And here's the voltages that's coming into your antenna. And if you just look from an S9 to an S1, the difference here goes from 2 millivolts, about 2 millivolts, to 200 nanovolts. That's 10,000 times difference in magnitude. Huge. And the different types of S meters. There's the analog S meter, which is, from a microamp meter, and you draw your various graduations on the scale, and it gives you an indication of your S meter. Or you could have a digital S meter where your bars are telling you, where you are in terms of your S meter. And there's lots of circuits around here that shows you, how to build an S meter. And there are people who are far smarter than me who've done this, and they've got circuits that work. And for example, here's a circuit up here. This looks like it's from a Doug DeMaw workbook or somewhere from that era. It could be from Wes Hayward's book. I don't know. But it's basically taken an analog audio frequency coming in, amplifying it, rectifying it, and then it's using a micro amp meter to show the relative signal strength. And this is how majority of S meters are done. They take an audio frequency in, and if you look at the early, renditions of the BitX, that's what was done. They took a analog feed before the LM386, and they took that and digitized it and was able to display what the signal strength was. In some cases, some people may take the input from the IF stage of your radio, and they may couple it with an AGC. Here's a Charlie Morris video where he implements this as a AGC. So it's putting out an AGC signal here, which is going to control the amplification of a downstream amp. And he's taking that same voltage and feeding it to a ammeter and showing the S meter there. Now the challenge in any of this is this is about 10,000 fold. So, and I think with these meters that you could get like a logarithmic nature. You got very small to very large currents. I don't know how these meters work. So I'm not going to comment on the good and bad of it. But if you kind of take a look and you look, let's just go from S1 to S9 plus 20. That's 20 dB over an S9 signal. And you look at the voltage that's coming in, just for that, it's 2,500 times. And if you plot the S meter, the S reading at the bottom and the voltage here, it goes up, in an exponential fashion. It's not a linear curve. It's an exponential factor. And especially down these two values, they differ by 10 dB. All these other values here, you'll see in a subsequent slide, they change by 6 dB. So we use logs to help us with this when we've got this large variation in numbers, and it compresses it down to make the numbers smaller, the variation to be smaller. So if we do the same levels, But now we use the dBm, because if you go back to my scale here, it shows you what the dBm is here, right? So if you just take the dBm signal here, which is a power reading, right, the power input to the radio, and you plot that, the dBm reading as a function of S reading, you get a straight line. And the benefit here, the variation is about 3 times. So 3 times 53 less than 3 times 53 is, 120. So it compresses the data you have to deal with, and you can get a nice straight line. So it's far easier to visualize this. And again, here, the key thing to mention here is these numbers differ by 6 dB. And I think 6 dB in a voltage, that's doubling the voltage, right? I think 3 dB is a doubling of power, and 6 dB is a doubling of voltage. So here's some approaches I looked at that I thought of, in terms of implementing an S meter, and some of them are silly, but I'm just going to mention in any case. So the first option here is, if you look at this as a traditional radio, you've got your antenna, you've got your bandpass filter, you've got your first mixer, you've got your IF filter, maybe some IF amplification here, and then you've got another mixer here, and that's going to bring it down to audio. It goes to your audio amp, and then goes to your speaker. So in terms of getting the relative signal strength coming in from your antenna, you could certainly look at the signal that's here after the bandpass filter. The issues with doing that, though, it's now you're dealing with an RF signal. So you've got a radio frequency signal you're going to have to detect. And it's going to be difficult to isolate the signal of interest, because, this band could be, say, 200 kilohertz or 500 kilohertz or something of that order. And so all those signals you're going to be detecting here. So you can't really look at the specific signal of interest. And it gets worse, because if you've got an RF amplifier at the front end here, a low noise amplifier at the front end, which the Phoenix does have, the reading you read here is going to be dependent on how much gain you've got here. So if you take a reading here and you change the gain here, this reading is going to change. So the next step is to do like what others have done, is just, especially for an AGC circuit, is to look at the signal coming off your IF filter. The benefit of doing this is that you're looking at about 3 kilohertz, 2 kilohertz of bandwidth. So now you're sharply focused on the signal of interest. So the downside is, many IF stages you're dealing with RF. You have to now detect an RF signal, and could be difficult. And same thing as with the other implementation, is if you've got an RF amplifier at the front end, you change the gain at the front end, that's going to change your reading here. So that's one option. The next option is to use the audio signal. So if you look at the audio signal coming out of the mixer, you're looking at this. All of a sudden now you're dealing with audio frequencies, which are relatively easier to deal with. And you could detect and amplify them a lot easier. However, same thing as all of the other detection processes, if you've got a RF amplifier at the front end here with a variable gain, that's going to change what you're seeing here. And in fact, in my ICOM radio, I've got a button that's got a preamp. I can't select how much gain I've got in my front end, but I can introduce a fixed amount of gain. And if I go and I change the gain, what happens is that the S meter reading goes up. So And the other thing that, depending where you put that, if heavens forbid you do your detection here, it's going to be dependent on your AF gain, on your audio frequency gain. So in terms of, this is the way I kind of thought about it, and I talked a little bit about this, is that, okay, so there are two ways of doing this. One is you need to measure RF signals. And the way you could do that, you could use a diode detector, but you got, fairly weak signals, especially if you're coming in from the IF stage. That's a fairly weak signal, down around, I don't know, maybe minus 50 dBm kind of thing, minus 40 dBm. It's relatively weak signal, so you're going to have to amplify it. And I've seen others do it using a diode detector. I've seen recently a video where this guy takes a diode and he was able to detect like very, very small currents. And it's a matter of integrating it over time, and you can get a fairly accurate reading. But to me, I think the diode, you need to get around that 0.7, or if you've got a Schottky or a germanium diode, you still have that forward voltage drop that you have to overcome. The other approach, which Peter suggested, is to use the AD8307, which is we use that in SNAs and power meters. That's the logarithmic power amplifier, and that goes down, I think, well down into the minus 70, minus 80 dBms signal level, and can go right up to, I think, like 0 or plus 1 or 2 dBm. So it's got quite a large dynamic range. The issue here is complexity, because all of a sudden you got to deal with RF. It gets complex. If you're using an 8307, it gets complex, but certainly I think it's going to be a lot more accurate. So if you use an audio signal, it's going to be simpler to measure and filter, because audio, you can basically use RC filters, right? However, I suspect there's going to be much more noise, induced noise, because if you go back to the little receiver, so now in your receiver, you're looking at the output coming out here, right? Let me expand this so get a good view of it. So you're looking at the signal coming out here. So each of these parts here, especially if you got amplifiers, they're introducing noise. So, the noise content you've got here is going to be dependent on all the noise of these stages coming in. So I suspect it's going to be a lot noisier detecting a signal here than it is here. You're going to get a lot lower noise. Okay, and lower complexity, but I have a feeling it's going to be less accurate, less sensitive, but complexity, it's not lower complexity, trust me. After going through this, it's not lower complexity at all. So, at this point, you need to take a step back, and this is what I did, and this presentation really helped me to solidify that, is that you got to take a step back, and you got to see the forest from the trees. And what's the goal here? And how accurate does this really need to be? And is an S meter a precise instrument? And you all know the answer to this. It's a relative gauge. It's not meant to be a precise instrument. So with that in mind, here's the final approach. This is how I decided to implement the S meter for the Phoenix. First off is to use audio. Take a look at the signal before the final AF amp. Apply filtering to clean up the noise, so that, because that signal coming out of the final filter, it's got mixing products. It's got both audio, but it's also got RF coming out. So you got to filter that junk out. And I'm not going to use a analog meter. I'm going to use a microcontroller. So I'm going to use the microcontroller ADC, digitize the signal, and display it on a bar chart. So I'm going to use a microcontroller software approach, and I'm going to try and reduce the hardware, because by using the microcontroller, I'm using less hardware. I don't have to implement a meter. I don't have to, play around with that. And I decided I'm going to use op amps. Keep it simple. They work, especially at audio. They work very well. They're well known, precise, and use that. So this was back in the grandfather to the Phoenix, the Dueling 612, the D6 612. This was how I implemented the S-meter circuit. So I took the audio signal coming in from the mixer, I fed it to LM386 with this pin here with a 10 microfarad cap across pin 1 and 8. You got the maximum gain coming out of this. Then I had a detector here, a diode detector here, and a capacitor to, convert the ripple coming off of this to a DC level. And I fed that to the ADC for the microcontroller, ADC of the Dueling 612. And it worked relatively well. However, it was a royal pain in the ass to calibrate and implement in software. So I decided to innovate. So in the Phoenix, I applied, I used 2 amplifiers. These are NE5532s. They're very cheap. And I basically used the amplification stages that Pete Giuliano used in one of his projects. He had an audio amplifier where he uses these amps along with a LM, I think it was a 380, not a 386, it was a 380. And, I think there was like a 2 watt. That LM380 was, I think it was about a 2 watt amplifier. So I just took those stages here and I put those, married those together, had a detector stage here. So I got only the positive going ripples, a capacitor to convert the ripple to DC, and I connected the ADC, microcontroller ADC. Okay. The issue was, now, when I was redesigning the Phoenix, every circuit in the Phoenix, every single circuit, I simulated in LT Spice, and I also built a proof of concept, a POC board. Okay, I built a proof of concept board, tested it, make sure it works, and then I married it together in the Phoenix. I did that all except for the S-meter. I remember having a conversation with Peter before we put this, sent this off to GLC PCB, is what happens if this doesn't work? And sure enough, it didn't work very well. Well, it didn't work at all, because the problem was it had too wide of a dynamic range. Because remember back here, when I came back and I said, look at the dynamic range here, because I'm dealing with voltages. So here, you've got a 2,500-fold increase in voltage going across here. And that amp, where's that amp? Right here. And that amp just couldn't support that dynamic range, because one of the reasons was these op amps were single-sided. So they were fed with 12 volts on the plus rail, and on the negative rail, it was grounded. And we had to put a bias. We had to put 6 volts here between the 6 and 12. So you got it swinging around the 6 volts coming out. So you only got a 6 volt swing, and the NE5532 is not a rail to rail op amp. So it's more like maybe, from 6 volts to 10 volts. So that limited the dynamic range of it. And the voltage coming out here, it was just too high for the ADC. I would fry the board. So this just did not work. And again, so I decided to innovate. I went back to the drawing board and I did some more innovation. I thought, okay, well, let me try a peak detector then. So this is in LT Spice, and I actually built this on a subsequent slide. I'll show you the data I got from when I built this, and I actually got some real life numbers. So right up front here, I put a low pass RC filter here to take away all the RF signals coming in. And by the way, the other amplifier here, I didn't have an RC filter here because I didn't need it, because these op amps here, I felt, they would do the filterings themselves, because these are audio amplifiers. So any RF coming into them would get attenuated out. It would not make it through. But in this version here, I decided to put an extra RC filter in, even though I know these are audio amplifiers, and RF would get, shunted to ground. It wouldn't be amplified. It wouldn't make it through. So I created this. Here's just a buffer amplifier. It's given me 5 times gain, and here's the peak detector here. And basically all it is amplifier, and you put a diode. And I'll explain in a second how that diode works. And what's coming out from here is this is following the peaks. It's following the humps. So only the positive humps are coming through, and this is following the positive humps here. And you put a diode here to smooth those humps out, so you get a little bit of ripple. And this resistor is to bleed that diode off, that capacitor off once it gets charged. And this I'm just simulating in this LT Spice simulation. This is the sample and hold capacitance of a typical ADC of a microcontroller. It's around 14, 20-ish picofarads. So I just put that in just to see if it's going to make a difference. So I ran my simulations. If you want to see how an op amp works, I encourage you to go back to my op amp video, which goes through, how an op amp works. So what I'm not going to explain in detail how the op amp works. I'm just going to talk a little bit about what it's doing. If you want to get deeper into this, go look at my prior video. So the way this works is you've got your op amps here. You've got Vin coming into the plus terminal, and your negative terminal is your minus terminal is connected to the output in a feedback loop. So the way op amps work is anytime the plus terminal is bigger than the minus terminal, the output goes towards the plus rail, the plus voltage source. That's called the plus rail, right? So it swings up there, and as this voltage difference, as long as it's microvolts or hundreds of microvolts, microvolts, this will swing up, and it just goes whoop right up, and it hits the 12-volt rail. It does it in a sort of a linear fashion, but it's almost like a straight line. So as soon as this terminal is larger than this terminal, this voltage here goes whoop, and it goes right up to 12 volts. And if you listen, you could hear the op amp making that noise. Whoop, you could hear it. I'm joking. So now the opposite, if the plus terminal is lower than the minus terminal, okay, the op amp goes whoop, and it goes down to the minus 12 volts rail. So this output is always going plus or 12, depending on if the plus terminal is greater or less than the minus terminal. So the way this works, so if you've got a signal coming in, initially, let's just assume this is 0. Okay, so 0 signal coming in, and all of a sudden, it starts going up. You got a sine wave. It starts going up. As soon as this creeps up a little bit, this comes up just a tiny microvolts. It comes up, what happens is this terminal here goes up to 12. And as this is a diode, and let's assume it's 0.7 volts. I think this is a Schottky diode, so it's probably like 0.3 or 0.4 volts. But let's just assume it's 0.7 volts, the voltage drop, or the forward voltage across here. So this diode only conducts if this side of the diode is 0.7 volts higher than this side of the diode. So if we've got a voltage coming up, and this goes up to 12, as it's going up to 12 volts, this goes up past 0.7 volts, this starts to conduct, it goes back around, and it locks the voltage in. So it locks whatever voltage here is. So let's just say it's 200 microvolts. Right here, it's going to be 200 microvolts. It's going to lock it in. Then if it goes up to 400 microvolts, same thing happens. This is now bigger than that. It goes up. The same thing happens. This starts to conduct. It goes back around and it locks it in. And so this is locking in whatever voltage here. And so what in essence is happening at the output here is you're only getting the positive going humps. The negative going hump, because this now, if it goes negative, this terminal is below that terminal. This goes whoop, and it goes to minus 12 volts. And now it's reverse bias. 12 volts, doesn't matter what's here. It's reverse bias. It doesn't conduct. Okay, so we've got a capacitor here that charges. Whatever voltage is put here charges this capacitor up. And as that hump increases, the voltage here gets stored on that capacitor. And in this circuit here, this capacitor does not bleed off, because the only way it can bleed, it can't bleed through the diode. The only way it can bleed is through this resistor into the negative terminal. Now, an op amp, if you go back, look at my videos, I'll talk about the input impedance of an op amp. It's very large, very, very large. And because of that, the current flowing into an op amp is very small. It's of the order of nanoamps to picoamps, very, very small amount of current. So this capacitor doesn't really bleed off. It bleeds off very, very slowly. And so right here, this is going to be now the peak, because as this comes up, as it follows the peak, it hits the peak, this capacitor locks in that peak, because as the voltage comes down, this peak remains on that capacitor. Okay, so this is the circuit I built. This is in KiCad here, and I milled the board. So you can see the RC filter here. Here's the amp, the front end amp, and I put a pot here so that I can control the gain. And here's the peak detector here. Can you guys hear me okay? I've lost signal here. Have I?
Yeah.
Okay. So you've got the peak detector here, right? And so what's happening here now is I put a Zener diode here. I put a 4.9 volt, and it was a pain in the butt finding a 4.9 volt Zener diode. Usually they're 5.1 volts, and I didn't want to put a 5.1 volt Zener because here's a protection diode to make sure this voltage here doesn't exceed 5 volts. I didn't want to fry my microcontroller. So that's just a protection diode to make sure this voltage doesn't go over 5 volts. Then you've got the capacitor here that charges and holds the voltage. And then here, remember I said the capacitor can't bleed through this path. So we have to put a bleed resistor here to bleed that capacitor off. So if the S signal changes, it's going to change in a relatively short period of time. And so that's it. And here's the other innovation I did was I used a negative charge pump. So this chip produces a minus 12 volt voltage based on a 12 volt input. So now my op amp had a minus 12 volt source for the negative rail and a plus 12 volt source for the positive rail. So the op amp could swing between minus 12 to plus 12, and you must have minus 12 to use this peak detect here. So here's the data that I got out of this. I actually built this, connected up, and I've got a video, and I'll show you how I measured this in a little while. But here's the S meter strength, and here's the dBm level. So this is the signal that got fed. This is not the signal that got fed in here. This is the signal that got fed into the Phoenix. This is connected to the audio output from the mixer. from the mixer that's taking the IF signal, and it's creating a audio signal to go to the audio amplifier. So this is what's feeding into the antenna port. This is my peak-to-peak voltage that I'm seeing here. This is the peak-to-peak voltage I'm measuring here. I'm measuring that with my scope. And then here I'm measuring the peak voltage coming off at this point with a meter. I just plugged in a meter and I'm measuring the voltage here coming out. And at one point I connected my ADC as well, and I converted the voltage to an ADC reading. So once I implemented this, I found that this is the only dynamic range. Because what happened, if I went above minus 70 dBm into the Phoenix, the peak voltage here was 4.7, which at 4.7, this Zener starts kicking in, and so it starts compressing, and I'm not getting a proper reading at minus 70 dBm here. So that was basically so roughly about minus 73 dBm was the top. Anything above that, it starts to compress. And then at the other end, I went down to S5, and if I went down to, say, minus 100, the output here was about 200 millivolts, but it was extremely noisy because there was a tremendous amount of ripple on the line here, and the ADC could not get an accurate reading of it. Even the scope, the meter, it's bouncing around. You know, this filter here was not working very well for such low signals coming in. So again, same problem as before, too large dynamic range and the voltage here exceeding the ADC. So this is no better than the other circuit I did before. So I decided to innovate some more, and I introduced something called a log amp to do a proper logarithmic measurement of the signal coming in to compress it. To actually not compress it, but to linearize it to get a less dynamic range. Looking at dBs, you still get the dynamic range, but the variation is smaller. So I implemented same circuit as before, implemented a log amp. Here's the log amp, and I'll talk about how a log amp works in a minute. But in this case, you've got the diode in the feedback chain. You're feeding back here, and you've got the diode in the feedback chain. And then I added, it turned out the voltages here were very, very small. They were small, they were compressed too much. And so I had to put a stage here. This is a non-inverting amplifier, and I'm getting about 5 times the gain here. Same thing again, I've got a capacitor, gets charged up, a Zener, and then the S meter here, the ADC there. So how this works. So if you look at this, same as before, if the plus rail, okay, in this case, the plus rail is 0, it's grounded. So in this case, if the minus rail, here, the plus input is at 0, it's grounded. The minus terminal, the minus input terminal of the amplifier, if that exceeds 0, it goes up. What happens? This amplifier goes whoop, it goes down to minus 12 volts. So this output goes down to 12 volts, minus 12 volts. Now, if this here was, say, let's say this is 1 volt, okay? This is 0, or this is, let me use a different number. Let's just say this is 0.1 volts. This is 0 volts. The diode does not conduct because it's not forward biased, right? But now, once this rail starts going negative, if I've got a small plus voltage rail here, this is going negative, it's now forward biased, and current starts to flow because the voltage here is lower than the voltage here. It's a negative voltage relative to this voltage, and as long as the difference across here is 0.7 volts, it's going to conduct. Now, the other thing to notice here is that we've got the input coming here to the minus terminal. Since the minus terminal has a very large input impedance, very small amount of current flows into the minus terminal. All the current has to flow through this diode. Has to flow here. It has to flow through there. So the current that flows through the diode is given by this equation here. And so this is the diode current. I naught is the saturation current of the diode, and that's fixed for a specific diode. It's a constant. NVT is a constant. That's got to do with the, I think VT is the thermal voltage, 0.23 or 0.25 volts or something like that. N is some kind of constant ideality constant or something like that. But basically, this has to do with the charge of the electron and Boltzmann's constant and the temperature in Kelvin. But ignore that. It's a constant. The thing we have to know is this is a constant. That's a constant. It doesn't change. The only thing that changes is VF, the voltage that's going to be fed into the diode. Now, if you do a little bit of clever math, you end up with this equation. And again, NVT is a constant. I naught is a constant. R is just the R here. That's a constant. So I naught R is a constant. It doesn't change. It's like 3 or 10 or 100 or something. It's a number. It doesn't change. This number doesn't change. The only thing that changes is V in, the voltage in coming in here, and V out, the voltage coming out here. So all of a sudden, we've now got the output voltage as a log of the input voltage. So we've got a logarithmic amplifier. And this chart is just showing that it's an exponential nature, why it's E raised to a power, because after 0.7, the diode starts to conduct in an exponential fashion. So if you take the log of this, you get kind of a straight line. So here's the data now. Here's the money slide. Here's the data, and I'm almost done. This is the data that I got after I built the peak detector log amp. So you could see, first thing to notice, look at the dynamic range. The dynamic range here has increased substantially. I'm going from an S1 to like an S9 plus 10. I'll talk about this in a second, but it's got quite a large dynamic range here. Here's the dBm. This is the peak voltage. So if I go back to my signal and I look at the peak voltage coming out of my peak detector, so I look at my peak voltage here, right? That's my peak voltage, and I look at the log voltage. So this now is the voltage that's coming out here. This is the log voltage here. So I'm measuring the peak voltage here with my scope, and I'm measuring the output voltage here. Okay, so you can see here, this is giving me values for the various numbers. And here I looked at the difference between the values because it should be about 6 dB difference. So the numerical value, now because of those constants and stuff like that, you're not going to get exactly 6 dB. But if you look at the difference between the two numbers, you'll see they're always about 0.1 something. 0.15, 0.16, 0.13. They're all 0.13, which is good. It means that I'm getting a proper deviation between the various S levels, which is what I would expect. Now, what happens down at the bottom here, S1, is down about a minus 120. I couldn't get it lower because 1.44 voltage was the lowest I could get it down. So even if I went to like minus 125, this would always say 1.44 volts. I couldn't go below that. So that was my lowest limit I could get to. Then at the top end, it starts to clip around S9 plus 13. So 13 dB above S9, it starts to clip. And that's because of my peak detector circuit, it's clipping. At that point, it's starting to clip, and I'm getting distortion. And you could actually see it on the scope. You'll actually see the wave becoming like a square wave. And you can see here the voltage. Here, it's staying about the same. So it's clipping. And the difference between S9 to S9 plus 10, it's 10 dB over. So it's not quite, it's 6 dB plus 4. So it's an additional 4 dB over. And you can see it's about a 0.23 difference. You know, if it was 12 dB over, then this would be 0.3 because it'd be double this, 0.15. It'll be about 0.3, right? So these numbers kind of make sense. So the dynamic range seems to be okay. And what, in a subsequent slide, I'm going to talk about this, but what I need to do now is just set what the lower limit is so I could get higher range at the top end. So calibration. This separates the men from the boys. So there are two ways that in software you could calibrate this. One is the simple ways that you feed in an S9 signal and you hit a button in the microcontroller and you say calibrate. And it takes an S9 signal in and says, okay, I know what an S9 signal is. And I know that if the signal drops 6 dB below that, it's an S8. If it drops 6 dB below that, it's an S7, and so forth. And that's what this algorithm is doing here. The other approach is a lot more complex, but it gives a very accurate reading, is that for an S1, you look at what the ADC is reading, you feed in an S1 signal into the Phoenix, you look at what the ADC is reading, and you say, okay, if my signal is that, it's a 1 bar, it's an S1. If my signal, then same thing with an S2. You feed in S2 and you say, okay, if my ADC is this, it's an S2, and blah, blah, blah. You do that for all your readings. The problem with this is that you would have to calibrate it with 11 data points as opposed to 1 data point. This is very complex calibration. This is a very simple calibration. So now I'm going to show you a video. So this is using the simple calibration method, and I'll show you the relative accuracy of it. So at this point, here's the S-meter board I made. You can see the 2 op amps here. It's 2 chips, but it's got 4 op amps. This is the first amplification stage. There's the pot there that's increasing the amplification at first stage. Here is the peak detector there. You can see the diode right there. Here's the log amp. You can see the diode there for the log amp. And then on this side is just a amplifier to get the DC coming out of this so the ADC can read it. This chip here is the voltage pump. So that's taking the plus 12 volts. This is coming in. I had to create a little daughter board here on the Phoenix so I could feed in 12 volts and ground to the board. So that's 12 volts coming in. This is taking that 12 volts and it's creating a negative 12 volts. So I got my negative 12 volt rail at the bottom here and my plus 12 volt rail at the top here. And this is the signal that's coming in after the mixer from the Phoenix. And this is the signal that's going to my ADC of my microcontroller. And you can see my scope probe there and where I was probing various things. So now in terms of the experimental, like the source, I've got my signal generator here, and I put 70 dB of attenuation on the input here. So whatever output I put here, I have to drop it down an additional 70 dB. So if I had minus 1 dB coming out here, the output here would be minus 71 dB coming out. So for the first test, I'm feeding out 14.1 megahertz, minus 45 dBm. You account for the minus 70 dBm, that's 115 dBm, which is an S2 signal. And here you can see it fluctuating. It's saying it's an S1 or S2. So here's an S3. And you can see it's saying S2. It's not quite coming S3. Here's an S4. So it's showing me S3 here. This is an S5. And there it's showing it's an S5. And again, this is the simple calibration. This is an S6. So there it's saying S6. So it's giving me a good relative reading, right? Here's an S7. Here it's showing it's an S8. Here's an S8. This is now saying S8. Here it's saying it's an S9. So it's a little bit off. Here this is an S9. It's saying it's an S9. So now this is S10. This is not 10. It's not S9 plus 10. Because I couldn't take it down to S9 plus 10 because it distorts. So this is S10. So it's 6 dB below or higher than a S9 signal. So it's an S10, right? So here it's saying an S10. And so anything above S10 now, it goes up to the next, it goes up to an S11. It goes up, it says S11, which is saying it's like, it's close to 10 dB over S9. Oops, so here now, here's the same test again, but now it's with the complex calibration software I'm running. Same test. Let me just skip ahead here. Same configuration. So here we go. So now here it's a minus 120 dBm. So this is like an S1, between S1, S2 signal. And you can see it's going between an S1, S2. Again, this is the complex calibration software. Here's an S2. You can see it's peaking at an S2. So it's saying it's roughly an S2. Here's an S3. And it's showing it's an S3. It's peaking out to an S3. This is an S4. So at S4, it's locked in. It's solid at S4. S5. Showing S5. This is S6. It's showing S6. This is S7. Are you guys still there? Are you guys still following this?
Oh yeah.
Yeah.
This is S7. Here's an S8. Showing S8. So you can see it's reasonably accurate. Not like the simple calibration, which was, it could be off by 1 S unit. This is like bang on. Here's S9, it's bang on. Now this is S10. So it's not a 10 over S9. So it's showing it's an S10. And this now, it's full strength. It's as high as it can go. And it's locked in at an S11, showing it's over 10 dB over an S9. So that's it. So, forest from the trees. What's the takeaway here? Okay, so going forward, I'm definitely going to use a peak detector with a log amp. What I need to do now is I need to limit the range that I'm going to be uh, seeing on the S meters. Like, I don't think it's practical to say I'm going to see an S1, because with the current noise floor around that we get, there's no way you're going to see even an S5 or an S4, because with the noise, typically the noise floor is like 6 or 7. For me, it's 6 or 7 noise floor. So for me to even see an S5, I can't see it. So I need to raise the lower limit so that I could get a higher limit. So I could see potentially an S9, a 20 dB over S9. So the way I do that is I'm gonna have to use less gain or no gain at the front end to allow a higher output, and maybe use a better op amp, maybe use a rail-to-rail op amp, but I don't think I need to. But that's kind of the takeaway for me, and so that's it. So let me stop sharing my screen. And back to you, Mr. MC.
Very good. Very interesting, Dave. Um, you were saying there at the end using rail-to-rail op amps. Isn't that what you were using?
No, they're not. The TLO72, the top voltage, I think it was like 10 or 11 volts. If you look at the data sheet, it doesn't go up to like VCC. Sorry, it doesn't go up to VCC. It goes to a volt or a volt and a half below VCC. And the same thing with the negative voltage rail. It doesn't go down to minus, what's it, VSS, or I don't know what it's called, VSS, I think. It doesn't go down to VSS. It goes to a volt or a volt and a half above VSS.
Yeah. Okay.
So
No.
rail to
Yeah.
rail means it swings all the way right
Yeah.
through.
Okay. That makes sense. Go ahead, Pete.
Okay, thank you, Dave. Most interesting. I like where you show alternative methods of doing this. At one point, I wrote down here, it says, well, the decision on what method you use is what parts you have on hand, whether it be the TLO chip or the 8307 or what have you. But I'm going to come back to the 8307, Dave, as you probably thought I would anyway. But looking at your circuits you've got in there, wouldn't the 8307 chip actually be a much simpler circuit, lot less components, and then you don't have the problem of dynamic range, because the 8307 will accept, say, down to minus 73 all the way up to a plus dBm volt level, right?
Yeah, what about cost? How much does an 8307 chip cost versus
For
a
me,
TLO7 chip,
hand,
which costs like 10 cents, 15 cents, 20 cents, or
well,
whatever, right?
I'll look it up. But the point taken, although I do have a couple of 8307 chips on hand.
Well, in that case, why don't you plug it into the IF stage and just look at the signal coming off of the IF stage? And Bob's your uncle. I wouldn't plug it into the audio end, because those chips I think are meant to be more so RF.
Yeah. Oh, yikes. Okay, you're not going to go to DigiKey for them.
Yeah.
Wow. Okay. I bought mine off of eBay and they seem to work. So don't go to DigiKey. They want $25 or something.
So I spent maybe on the those circuits, if you're ignoring the cost of the mill to mill it, if you ignore that cost, I may have spent maybe $3 total.
Okay, I understand. Okay, understanding that, fair enough. Just a couple other more points there. I vote for the complex calibration, by the way. And I think with the Phoenix, I have a lower noise floor than you do, but I found that I think S4, I think at one point, if I really strained hard, I could hear an S3 signal, but boy, it was hard work to hear it. So I think S4 is the best that the Phoenix is going to signal that is going to hear. I noticed on the Phoenix board, it looks like you got another daughter card in there.
Yeah, as I said, that's a power supply. That's just taking the power off of the relay. There's a power relay.
Yep.
So I lifted the power relay and I put a daughter board and I plugged the relay into that daughter board so I could siphon off 12 volts easily, as opposed to going and soldering to a pad and lifting it, because I don't want to. These boards you get from China, you have to be really careful how you solder, because the pads will lift if you use too much heat.
Okay. What do you think is a better method then, Dave? Or it doesn't really make any difference, cost aside? Pulling off of the IF or audio?
For me,
No,
audio. I'll do it.
Cost aside.
Because Peter, end of the day, forest from the trees. That's why I was saying, what's the goal here? Are you planning to get a 3.569 dBm reading, or you just want to get, roughly it's an S3? It's an S meter. It's a relative reading. You're not looking to get an accurate bang on. You don't want precision. My ICOM, I'll guarantee you, my commercial ICOM I've got here, it's probably got a little bit of a deviation. So even if it's a S5 signal, I bet you it may say S5 in my rig, and you take it to another rig, it may be going to maybe an S4, peaking to an S5, or it's. I don't think it's meant to be a precision, accurate reading.
No.
Okay. All right. Thank you, Dave.
Okay, go ahead, Dwayne.
Yeah. Have you thought about, you're talking about rail-to-rail op amps. I've used something similar to this for other things, and I just use an MCP 6002. It's a rail-to-rail op amp. It has a maximum voltage of, it runs off of 5 volts directly with a 5-volt output. Makes life real simple. You could probably just go with the do away with the peak detector. Just go with a input log amplifier and a buffer amplifier in the output, and feed that directly into your ADC.
I'm muted. You mean use a diode detector, get the DC voltage, and then use a op amp, a log amp for that?
Yeah, just do that.
Yeah. What happens though if it's a real? Because and Dwayne, yeah, it certainly a good idea. The only thing I would be careful of is how low the signal coming in is going to be, right? Because I would have to scale it so that I'm getting a voltage between, say, 1 to 5 volts kind of thing, right, for that range. Because if it drops too low, I don't know if it might be too low to process.
I mean, if you're running a diode detector, you can put a little DC bias on the thing and drop the diode, and eliminate the voltage drop on the diode, so you'd be able to go directly into a log amp. Like I say, like I use the MCP 6002. They're under $1 a piece.
Yeah.
Yeah, and then they run, just ground in 5 volts, gives you a 5-volt output because it's a real device.
Yeah, and I think part of the problem we have here, Dwayne, is that the output that's coming into this system is too hot. So I think something like what you're saying to do may just work, because our output coming in is too hot. Because I had to turn off all the gain on that amplifier at the front end. I could basically lift that amplifier out, and because it was running as a buffer amp, basically, right? So ideally, you'd probably want to put a pad in there to bring the voltage down. So probably what you're saying would probably work better, given that the signal coming in is pretty hot.
I mean, it's coming in like that. All you have to do is put a pad on there. Since it's it's on the output stage, impedance doesn't make any difference. Just put a pot to adjust your
Right.
level.
Yep. 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 That's a good. Suggestion, Dwayne.
Okay, Ken had to disappear for a couple minutes. I'll make another comment, Dave. You mentioned earlier about your op-amp video, going through the active probe, and I was looking at the op-amps on that. I took a look at your video, and it was interesting how when you're working with something and then you read about it or listen to it, it starts to sink in a lot better. So yeah, you're right. Take a look at your video; it's pretty good. Is there any other comments or questions for Dave? I thought I had another one here myself. I made lots of notes, Dave, but okay. Well, thank you very much, Dave. Most interesting, and then it's nice to, like I said earlier, to see a few different ways of doing something, and then Dwayne added another dimension to it as well. Decisions. Are you going to send off? So is your circuit finalized now that you're? I guess the daughter board, is it going to come from JCPL, PCB, whatever they're called?
No, I'm done, Peter. I'm done with this. So I'm just going to get the S meter circuit I got working, and I'm going to 3D print a case for this, and I'm done. I can't. I've been working on this now for like what, 5 years, 6 years. So I'm done. So once I get it working, and I got a proper S meter coming in, TX looks as if is working. So the only thing I want to do is I've made digital contacts, is I want to make a phone contact on it. So once I've made a phone contact, it's going away on the shelf.
Oh, I thought you were going to sell it to He Who Must Shop.
Yeah. Yeah, it's going into, I don't have as nice a case as Frank, where he's got all of his nice kits on display. This one is going under as a doorstop,
Okay. All right. I got a comment on a different subject now. I sat down with Peter Taylor, who did our SOAREX website. And if you recall, we just basically did a placeholder up there. So we had some information about us, so that when we went to Dayton last year, we could point to that site. And so I sat down with him last week, and just to go over a few things about, maybe making the better use of the website. And what I thought of doing was taking PDFs of our presentations and PDFs of any notes that you would have that went along with the presentations, and we would upload them to the website. So I've got a couple up there now that I have done, just to try and get a handle on how to do it. I'm not sure what else we could do with it. So if anybody's got any ideas, speak up. If somebody would like to look after this, now we're not looking for somebody to develop the website. Peter's more than happy to do that, but it's fairly easy to add a page in or anything like that. But maybe if somebody wants to take on being the idea guy for the website, or take on uploading any PDFs of our presentations, well, let me know. I think that's about all I've got for regarding to the website. Any comments from anybody? How come I can't see anybody? Turn your cameras on. I want to see all the hands holding up here to volunteer to do this. Okay.
Oh, Cherry turned.
Where's everybody's hands? Nobody's hands are on the screens. Oh, there's Al. Oh, you're just scratching your head. Oh, I thought you were putting your hand up. Oh, darn. Okay, is there any other comments from anybody else on any subject for that matter? I've kind of divorced myself from LT Spice for a little bit. I had to take a break from it. But I think I'm getting close to actually getting maybe a milling a board for the active probe. I probably still do a little bit more before I get around to doing it, but I think it's going to work out pretty good. And what else? I think that's about it for me on that. To comment on that. I know I see Ken's back, so I'll turn it back over to you, Ken.
Yeah, I gotta go. Just a quick thing I had posted about the Cork Hamfest in October.
Yep.
So far, I think Eric wants to go, and it's on October the 14th in Kingston. I intend to go regardless. So, to get away.
Hey,
anyways,
and Kingston's sexier than Hamilton anyway. Who wants to go?
Yeah. When's the Hamilton one?
This Saturday.
Oh, okay. No, I can't.
Anyone going there?
No, it's next Saturday.
Oh, yeah, next
Sorry,
Saturday.
yeah. Sorry, a week from Saturday.
No, I can't go, unfortunately.
Peter, you're planning to go?
What, to Hamilton?
Yeah.
No.
Okay, guys, I gotta go.
Yeah, take care of what you need to.
Okay.
Thanks.
Have a good night, everybody.
See you, Ken. I'm keeping my fingers crossed I can even go to the Kingston one.
Oh, you'd have a hard
Right
time
at your
dodging that
doorstep,
one,
right?
Peter.
Well,
I
we
plan to go to the Kingston.
I said to Eric and Dave, we got company coming over from England, so I'm not exactly 100% sure what the plans are. What I'm hoping for is that whatever She Who Must Be a Base got scheduled for this that weekend, I can get away for a few hours to go to the Hamfest and then go wherever they got planned. So anyway, that would be
out of range of your scooter.
Pardon me?
I thought it was out of range of your scooter.
Nah, I'm a funny guy.
It's my scooter. It's at Lake Ontario Park, isn't it, Peter?
That's right. You got. Pardon me?
Is that Lake Ontario Park or 560 Legion?
It's at the Legion.
Oh, well, that night we're going to nominate you as president for Cork, eh?
Yeah.
Excellent.
Well, if he's not there.
No, I can't. I cannot attend Cork meetings because Cork meetings is on our SOAREX meeting night.
Well, you can just do it by Zoom.
Two
Just have
computers.
screens going, two
Yeah.
cameras, two screens. You know what?
One eye there, one eye
Like Dr.
here.
Kali Gupta.
Yeah,
Come on.
They're trying to-
multitasking.
Come on, you're retired.
That's okay,
you know,
Peter.
out of the world.
That's okay, Peter. For the entire month of August, I had to obey She Who Must Be Obeyed because we had relatives come in. So that was me in August. So
Yeah.
I feel your pain.
Yeah, but he's not doing a whole month.
Yeah.
Yeah, I had to do a whole month. Well, almost. It was like 3 weeks.
Close enough.
Anyway, well, time's here 10 to. So I guess that's pretty much it for the formal meeting. That's
I'm never going to trust an S meter again.
I'm sorry?
I'm never going to trust an S meter again. When I realized what's actually should be involved, I've heard about people talking about this for years, calibrating an S meter. And I was always very suspicious of S meters in general. I don't consider them to be very reliable. But after watching Dave's presentation, I'm going to treat them as an on-off indicator.
No, but just to interject here, Dave, when you showed your complex calibration routine, yeah, that's accurate because of what you're making a specific measurement and saying that specific measurement will be that instead of doing a generalized thing. So that would be an accurate way, but I don't think industry does it that way.
Yeah, but Peter, what's a S meter? Why do we need a S meter reading? Why do we need it? Do we even use it?
No, I'm
No,
not.
because if you recall,
I don't think I've ever used it.
If you log a message, right? It's always 5.9 or whatever, right?
Which is
not
even more
using it.
Me telling you you've got your 5.8 or 5.7 or anything like that is probably more suspect than what the S meter would be.
But does anybody actually use their S meter when giving that report? Is that the intent?
I guess it's a guideline.
I thought it was just a relative scale. You're getting the guy's signal and he's, on a scale of 10, he's a 5. That sort of thing.
The only thing I ever really used the S meter for, really that I really paid close attention to, really was the noise floor.
No, I do the same thing. My only thing I read about with an S meter is the fact that my noise floor is S7 on 40 meters.
Move.
And you're
On a good night.
into that. That's all. It's just SNR.
Yep.
Well, at least you have an antenna up to hear all that noise, because Eric doesn't have an antenna to hear anything.
What still?
What's an antenna that you talk about?
Wait a minute. You have a metal roof on your barn. Hook up to that.
That might be coming. Yeah.
Tune it up. Tune up your roof. New meaning to the term NVIS.
Yeah, that's right. Yes, it is an inverted V after all in the barn. So
it is.
Yeah,
just
that's
tie
right.
into the center.
What's the worst that could happen? The chickens would double up their egg laying routine.
Well, we do have a new cat named Demon in the barn, and he might have some objections.
Just put a bolt through the roof and put 50 ohms on it. See what happens.
Cherry, you plan to go to Kingston Hamfest?
No need to ask.
I didn't. I know I didn't have to, but you're quiet, so I thought I'd better ask.
Yeah, unfortunately, I'm not able to go to the Hamilton one because I don't have a vehicle that day, unfortunately. But I will be there in Kingston. Yeah.
What kind of radios you looking for, Jerry?
Oh, just shopping around. Yeah, most of the time, smaller stuff. Yeah.
He's slipping. He's becoming an Eric. He's going to be the new Eric.
Well, Eric's coming, isn't he?
Yeah, Cherry, do you want me to pick you up on the way? I'm coming from Caledon to Hamilton. Oh, look at his face go serious. Look at that. Wait. Anyway, so we'll talk.
All right. Okay.
Time to dust off the boat anchors if all these out of towners are coming to Kingston.
They can help me rake up the leaves. Anyway. All right. Well, I guess if anybody else has any other comments, I guess we've come to the end. So thank everybody for your participation. Dave, thank again for the presentation. And we'll catch up with you next month on
the 4th.
The 4th of October. Very good.
Yep.
And let's see who's doing the 4th. It used to be me, which means it's now Eric. Okay.
Yep. That's right.
Okay. We'll see you guys then. Cheers.
All right.
Good
Dave.
Bye, everyone.
Bye.
Night.